continue this discussion of motivic spaces. So let's do a little recap maybe. What is our goal? Our goal is to define this category of motivic spaces, which is meant to behave somehow like, if this was topology, this would just be, the motivic category of spaces, which eventually will be replaced by spectra, and we're looking into the algebraic geometric analog of space, if you like, which is why they call motivic spaces. So I defined this category for you. So S is an affine scheme. And we define this, and then we have a choice of topology. So we can say it could be in this Motivic topology, the État topology, or their pro variant, pro Motivic or pro État. And in the case of these pro things, we will look at these weakly smooth affine schemes over our base affine scheme, whereas in this case, we will look at just smooth affine schemes. This weakly, I remind you, you can think of it as being an appropriate generalization. So these are exactly the finally presented objects in here. And these are defined by a certain lifting property that maybe I will talk about later again. So this is sometimes the geometric objects that we want to include. And then this category motivic spaces was defined to be the full subcategory of free sheaves on weakly or non-weakly smooth affine schemes valued in anima, and this is the full subcategory of free sheaves that are at the same time tau sheaves and also a one variant. Okay. So that was the definition, and we had observed that this inclusion admits a left adjoint, which I call L mode or motivic. So this you can think of enforcing both the sheaf condition and the A1 invariance, and we have this the motive or the motivic space associated to some scheme. I think I should change the camera. But now, no, that's the wrong one. Yeah, thank you. Yeah, if it happens again, please tell me. But I think for some reason one of these cameras works and the other one kind of only works every now and then. Okay. Anyway, so we have this localization. The motivic spaces are this full subcategory, and this inclusion has a left adjoint with the localization enforcing these two conditions here. And we will say M or MS if we want to specify the base is this functor from weakly or not weakly smooth affine schemes. So we have Yoneda embedding into this three sheaf category. And we have this localization, which brings us to this category of motivic spaces. Okay, good. That was the definition, and we talked a little bit about the basic functionality. So for a map from S to T between two affine schemes, we have an upper star functor, which is characterized by saying the motive of some such weakly or not weakly smooth scheme over T is mapped to its pullback. So that was an easy functor. This has a right adjoint, which is also easily basically given by decomposition with this pullback on the level of pre-sheaves, and if F is weakly or not weakly, depending on our choice of topology, smooth, then this F upper star has a left adjoint F lower sharp, which again is defined by which you can understand what it does on these motives here. So it takes the motive of some such smooth thing over S and just takes that same thing, but now regarded as a scheme over T. So this is all nice and well, but like I said last time, none of this is so far really using the specifics, neither of that we have these kind of schemes more than we use these particular topologies. So now we will come to a statement that actually, that does make use of that. So this is the so-called localization. So what's the purpose of this thing? The purpose is to relate sheaves on some scheme and or Motivic spaces rather on some scheme to the ones on an open on a closed. So we will consider the following situation throughout, unless I say something different explicitly. So we will consider the closed embedding I of some Z into S and its complement J, which is S without Z. And we assume, Y we will see later, but we will assume at some point that J is quasi-coherent. Okay, so it's totally fine to focus on the case when S is an affine scheme, and then this is defined by a single element here of that ring, and this is the complementary localization. Yeah, so you don't really lose anything if you just focus on that case in your mind. And so there is a first step that I will have to do, but that I want to do really, really briefly. So because it's kind of formal and boring. So there is a function extension of, so far we have constructed this functor which I call H upper star, which takes an affine scheme and sends it to this category of Motivic spaces, and to map F it maps to F upper star. Yeah, this is what this notation here indicates. So we have so far constructed this thing on affine schemes, and now of course it's desirable and natural to ask this to exist in the greater generality, at least of all schemes. Maybe where's the sponge? It's going to be a tricky lecture. What? And then the lower border, right? Under the lower border. Oh, thank you. Yeah. So it's very desirable to have this functor in the generality of at least all schemes or even all pre-stacks. So let me just say, because it's very important to very similar to what we said yesterday. So we can extend this functor like so. So we have affine schemes, and we have pre-stacks. So this means it's just functors from affine schemes of the anima, right? And this is the Yoneda embedding. So we have a functor like this, which we constructed. And we want to, I don't know, I should put the op here. So, yeah. So we have a functor like this, and now, maybe let me not put it here and rather put H. Let me put the op here and write R there. Using the functor theorem, we want to extend it. So this is this Kahn extension. So in other words, this is the unique functor that takes a pre-stack, which is just such a pre-sheaf of anima, and represents it as a co-limit of representables. Here you have some F. This F is going to be the co-limit of representables. So maybe let's say Y of little s. So the s's will be living here, and this is indexed by just maps from these things to your F. So in other words, sections of this pre-sheaf. So this will be sent under this Kahn extension to the limit of these H stars of S, where the limit is taken by, you take the star pullback functors along these things. So yesterday we had seen that in the context of in schemes this is problematic, but for the moment we just want to have a cheap way of of seeing that if we have any scheme, we can talk about Motivic spaces on that scheme. Yeah. So this is what we'll do. In the notes, I have elaborated a little bit on this. I don't want to focus on it too much right now because the content of this localization theorem is basically already fully present in the case when Z, S, and U are all affine. Yeah. So you don't really lose all that much. So good. Let's say this, and now I want to state the localization theorem in this generality. So sorry, I said it, but I didn't write it here. So this S is now a scheme, yeah, and these are closely open subschemes. But again, the case when all three are affine is just interesting enough already. So here is the theorem, which goes back to Morel and Blavatsky. In the case of the classical situation of fluid schemes and so on, and has really been revisited time and time again. So, for example, by Kahn, and also there's a good exposition of this by Hoywa in more general situations than the ones that Blavatsky considered. And this also appears in the recent paper that I already mentioned by Remy, Scholbach, and Wolf. So it's really, I'm not claiming much originality at all. It's just that we will really try and say this in this utmost generality. So what is this theorem? So pick some Motivic space on S. Okay. So this is our ambient scheme, if you like. And now we have the following thing. So we have this sheet F, and we can do J lower sharp J upper star F. And here we can go I upper star I lower star I upper star F. So we have these unit and pro-unit maps. And here we also have something, namely, here we can do J lower sharp J upper star I lower star I upper star F. Yeah, so we certainly have all these maps. And this here we can compute. So this, by definition of what these functors are, this you can cancel this. So this you will see this is just J lower sharp of you like the point. Yeah. So using this base change along this open embedding U. So we have this diagram, and the claim is this is a co-Cartesian diagram in HS. Okay, so the statement here is a little bit careful. So what you mainly want to view this as is kind of an exact sequence. You want to say this is the extension by zero of coming from U, then you have the original sheet, and then you have the part living on Z. So you kind of would like to say we have this exact sequence, but in this generality of sheets of anima, one has to state it that way. But that's basically the gist of the statement. It's maybe I should say push out. Or co-limit. This is the co-limit of co-partition is fine. It's just Okay, so this is the statement, and before we prove this, I want to say a few words about what this by does. So it will always be under this assumption here, so I will not repeat this assumption, especially this quasi-compactness all the time. But let's somehow test a little bit what this tells us. So the most obvious corollary is the following. So if J is empty, or let's say if U is empty, right, that means Z and S are isomorphic up to reduced subschemes. So for example, Z is here in the notes it's a different letter, but let's say S reduced. So in this case, we have I upper star. So this will be an equivalence between HS and HC. Yeah, because in this case you see, this goes all the way, and then you just have this isomorphism there. So that tells us we have the equivalence. That's one thing. So in other words, this category of motivic spaces doesn't see, sort of it only sees the scheme as a topological space in the sense that this invariant here holds true. And you should think of this as compare as the following fact. So if you look at étale schemes over S, then again, there is a statement saying this is equivalent to étale schemes over Z. So this is the so-called topological invariance of the étale site, which is a classical statement, again, in this situation. And there is also a similar such statement about weakly étale sheaves, weakly étale schemes due to Bad-Scholze. And we will see how these things actually sort of fit into the proof here. So it's more than a parallel. It's really somehow, in some sense, you want to say more or less this implies this. I mean, up to additional arguments, but sort of it's a key part of what we are going to prove here. So this is interesting to know. And on the other hand, sort of this is a difference. This is different from, or different than let's say, derived category of quasi-coherent sheaves, right? There, it's decidedly not true that if you have some scheme which is not reduced, for example, and it's reduced closed subscheme, then QCO will certainly see the difference between them, right? So that is the difference. Okay, so in that regard, even though we always like to think about, just six functor as a very general paradigm, and it is, but already there we will see a marked difference between motivic sheaves and quasi-coherent sheaves. Okay, another thing that I want to say is it's a little bit annoying to always carry around this extra term there at the bottom left. So I want to kind of present another a variant of this, which turns out to be slightly more useful in the end anyway. So here is a variant. So let's consider pointed anima. So I write anima point here. This is just anima over delta zero. If you delta zero over, that's what's called. Right? So just somehow delta zero point into your thing. This is a point anima. And we have an adjunction between regular anima and point anima. So you can forget this base point and you can add one. So this is just, you take your thing and adjoin an extra base point. So this is certainly something we can consider. So this is how we'll move back and forth between them. And we will introduce this pointed category H bullet of S. This is defined, let's say, as pre-sheaves, again, on this weakly smooth affine over S. Now with values in pointed anima, satisfying the same conditions. Yeah, satisfying being a sheaf with respect to this topology that we choose and being A1 invariant. Yeah, so this is just a pointed thing here. And one can check, this is a useful thing to observe. So it is true that this pointed category arises from the unpointed one in a very somehow categorical way. Namely, you take this HS. So we observe this is a presentable category, so you can tensor it with something else. So maybe I write for emphasis tensor over anima, even though this is the monodic unit in PRL. And I tensor with this pointed category. So that's what one gets. And why is that a useful thing? That's useful because all the functors that we had on the level of this HS can then be propagated to functors on the pointed thing. Yeah, so we'll get, let's say, F upper star. Maybe I write once, but never again, this bullet here. So H bullet, for F from S to T, H bullet T to H bullet S, and this is kind of, you take the original functor and tensor it with the identity on the pointed anima. So that's one way to see it. The other way would be to say that in this pointed category of motivic spaces, you have kind of you have a natural functor from H bullet here, which just takes again something and adds this base point, and so the functor F upper star will be compatible with the original one by adding this base point and so on. Yeah, so this is how useful.
Tensor product is the one here. Then.
Yes, tensor product in TRL, and as I said, anima is the monoidal unit, so you can, if you like, not write it. Okay, so why do I mention that point situation here? I mention it because this properties of this function become a little bit better even in that pointed situation. So yeah. So another fact is that anima pointed is again a symmetric monoidal category, and I'll write this the symbol wedge for this. So what does that mean? So if you have two such pointed guides, then A wedge A prime is basically the push out. You take somehow your point and push out for a diagram point maps to point times A prime, and on the other hand you have A times point, and then the push out of this is this wedge product. Yeah, so you somehow no wait, that is not quite right. Sorry. It is it's the colimit of this diagram. So you take this and you collapse this these two sort of axes, if you like, in this product. Okay, so this is how you do some questions.
No, it's just fine. We're just discussing what the point is, but that one is clear.
Yeah, so this is just point is the final object. So this here is the final object. This is, if you like, M. So this now is on U here, point U if you wish. So MU of U. The base scheme. Okay, yeah. Good. So this is symmetric monoidal, and why do I bring this up? So I bring it up because for any map F from, let's say, F to S here, we can contemplate. So we know this F upper star is symmetric monoidal. Okay, and that gives us a map, a projection formula type map, and so which is something like this. So F lower star F wedge G maps to F lower star F wedge upper star G. Okay, so this is just the general formal nonsense, right? That the right adjoint of such a symmetric monoidal functor will be coming with such a map here. This is in general not an isomorphism. Yeah, so this is just some map, which is kind of telling you this functor F lower star is less linear, if you like, to say it that way. Like meaning you have these maps, but not generally asserting it's an isomorphism. And now one other consequence of this localization theorem is going to be the following. Corollary again of the localization theorem is the following. So we now focus on the case for F being equal to I, a closed embedding with quasi-compact complement, like I assumed in the beginning. Then we can consider this map I lower star from this pointed category on Z to the pointed category on S. And we will, so for this thing, this map here, so for FB, so this map is actually nice enough. The map star is an isomorphism. Okay, so in other words, if you like this way of talking about it, this I lower star is this functor is H bullet of S linear, where H bullet of S acts on itself because it's a symmetric monodic category. So this is, I mean, very much like what I just did an hour ago. It acts on itself because it's symmetric monodic category, and it acts on the other category, on H bullet of Z by Motivic. Yeah? So where H bullet of S acts on H bullet of Z via I alpha. So that's what this here is. Okay? So we will also say the projection formula holds true for such closed events. Okay. So how is that a corollary of that theorem? So we want to, like I said, we have the natural map. We want to check it's an isomorphism. What we can observe is that the functors J alpha star and I alpha star, they are jointly conservative. So if I have a map between two sheaves, two motivic spaces that are isomorphisms on U and on Z, then it will be an isomorphism. And so now I apply this to this map here. So I do I alpha star to it in J lower star. So let's do the J lower star first. So both of these pullback functions are noted. So J lower star applied to this, with this now being an I in J alpha star. J alpha star, yeah. Did I say J lower star? So J alpha star applied to this. Here we get, here we get, like before, we get point, and here we also get point, so that's fine. What about the I alpha star? If we do I alpha star, then we have I alpha star of this guy, which is F, wedge I alpha star G, and then similarly here. Yeah, so this is a direct consequence. So in other words, this is the first instance of a situation where this right adjoint is behaving somehow a little bit better than we might otherwise expect. Okay, so this gives you a little bit of an idea why this could be a useful thing, and we will now want to move that and see how this goes. It's a bunch of steps actually, all of which are, have a certain amount of formal nonsense and a certain amount of geometry. And I'll try to focus on the geometric somehow, salt in the soup, let's say, as opposed to the rest of the more formal ingredients. So what are we trying to do? So we are trying to show we have this push-out diagram here. There's two steps involved. One is we will reduce to the case when F is actually representable. Yeah, it's a representable pre-sheet. That will require us to do the following. So we know that any such motivic space is a co-limit of set representables, right, by this Yoneda type thing. So we'll have to see that all these functors preserve co-limits, which is true for these two left adjoints and also for this left adjoint, I alpha star, but we don't yet know about this I lower star. So we have to check this preserves co-limits in an appropriate way. And then we will be looking at the case when this is a representable thing, and then there will be some other geometric arguments coming. Okay, so first step is the following statement here. So you can think of it as some sort of an exactness of I lower star if you wish. So the precise limit is B functor I lower star on H Z to HS preserves not all co-limits, but almost all, namely all contractible co-limits. So contractible means, so you have a certain indexing category that indexes your co-limit diagram. This could be an infinity category, to which you assign this sometimes called, or like this. So you basically formally invert all. Maybe that's not a good definition. So you formally invert all arrows. So you So you form a groupoid by inverting all arrows, and you want this resulting groupoid or animal to be is then contractible. That's the thing. And, so the and like I said, there is two parts of the argument. One is a geometric argument, which I want to present, and then there is some formal nonsense which I prefer not to present. So what is the interesting geometric input? And now you will really see how this uses this interplay of weakly smooth and so on. Yeah. So I will only explain this in the case of these protopologies. If in the classical case the argument is similar, slightly more delicate because you have to always keep track of these finitely presented properties. But let's not worry about this because this exists in the literature. So proof for how this pro Motivic or pro entire, which means that we have to consider these weakly smooth schemes. Okay, so what's going on here? So let's consider weakly smooth schemes over this S, and then we can, like I said last time, go do the pullback and restrict to weakly smooth schemes over Z by so I write high upper star, but this really just is the final product. Right. I just realized I've forgotten to first do the reduction to the case when S is affine. So maybe I will do this now. So we are trying to prove this kind of statement here. Okay. So for not necessarily affine S, but by the definition of this H1 general schemes, this is and by Zariski descent of this H1 affine schemes, one can see that this statement for general S you can pull back to all these affines mapping into S, and then it reduces to such a statement. So let's say proof. And maybe let me just write it here. So I think I'll add this in the notes. Without loss of generality, we can directly assume S is affine. And therefore Z holds affine, and then I'm in the situation of the lecture of last time. So this represents some T to T times S. See, so we have this thing. So okay, but what is special about this is like I said last time, the image of I upper star generates this target category under retracts. Yeah, so in other words, every weakly smooth scheme over Z is, if you like, the special fiber of something living over S up to this retract. So it generates the target under retracts. Okay, and of course these retracts are really harmless. So you can sort of pretend everything in here was the special fiber of that. And that's actually the key geometric property. And a similar such statement also holds for smooth and without this weakling in front, but there it's more difficult. So we saw this particular assertion last lecture. I remind you, it basically used as a key input that these guys here are pro-eternal over some possibly infinite dimensional affine space. This affine space has no issue in lifting to S, but then the additional thing is this pro-etal thing over that affine space could be lifted using initialization over there to S. Yeah? So that was the input there. Okay, good. So we have this, and this implies that this function I upper star is what's called topologically quasi-continuous. This is a notion that's maybe not so widely known. What does this mean for some T in So we take some such weakly smooth thing over S, and we consider it a pullback given, and we cover it. We cover this thing. So given a covering sieve, let's say R. So we decide on we pick a bunch of pro etal or pro Nisnevich, covering of this special fiber under our pro topology, and then the collection. Yeah, so these, think of these are now schemes over this TZ, and a priori there's no reason to be extendable, but this thing does tell us it is true. So the collection of let's say T prime to T in my category weakly smooth over S, yeah, such that T prime Z T Z factors through this covering is actually also covering, is itself a covering. Yeah. So, morally speaking, you cover this special fiber in pro-etal or pro-Nisnevich, and thanks to this possibility of extending it, you will be able to hook up a covering of the T itself, which kind of restricts back to your original covering, roughly speaking. And this is what this property here is. And then there's general nonsense, let's say, that tells us the claim follows from there. So this is, in the notes I have a reference of this paper by Adil Khan, but this is really a categorical thing that I will try not to get into. But the key geometric input was this ability of lifting weakly smooth schemes over Z to ones over S. Okay, so that's what I want to emphasize. Okay. All right. So now I want to say one word here. I was stating this only for the contractible colimit. So what is an example of a non-contractible colimit? It would be the empty colimit, right? If this idea was empty, then this is, not contractible in the sense that contractible means, weakly equivalent to a point. So let's briefly contemplate on this example. So the initial object, so we have this HZ. In here we have the initial object. What is that? Well, this is this MZ of the empty scheme, right? And so now let's see what happens if I do this push forward. So I lower star of this, here in the notes I wrote HZ. Yeah, maybe I can. It doesn't really matter. This is not specific about whether or not I localize one and so on. But anyway, let's have a look at this. So this I lower star of this HZ of empty set. I claim it receives a map from the initial object on S first, yeah. But this is not usually an isomorphism. In other words, this I low star does not preserve the initial object. It's not an isomorphism, as you see by evaluating this on S here, right? So evaluate on, sorry, did I say S? I meant U. I evaluated on U, right? So it's not an isomorphism. If I evaluate it here, then here I have, here I have just maps sort of from, if you want to write that very slowly, from the empty scheme to U over S, of which there's exactly one, yeah, because confirming that it is an initial object. Whereas this thing here, I low star HC of empty set of U is HZ of empty set of the intersection of U with Z, which is again empty. No, sorry. I apologize, I made a mistake here. This was the other. I mean, that would have been this, but what I get, of course, by this representative maps from U, or at least to the empty set. And there is, unless U is empty, there is no such maps. Sorry. Whereas here now we do get, if you like, POM from Z over Z from empty to empty, and here we do get a map, namely the identity of the empty set. And so you see this is not the same. Okay. So this is just to explain why there has to be some condition, and we will see, well, maybe or maybe not, depending on how much time I have, sort of that how this failure of preserving the empty set or the initial object can be cured in this pointed situation, and then together with that statement, it tells you that in the pointed case, this inostar preserves all coordinates. Okay. But anyway, so this is a small little thing here, that not all coordinates are preserved, but almost all, we want to say. All right. So, like I said, the benefit of that proposition there is that we reduce ourselves to an easier case. So by the proposition, it suffices to prove the theorem for what? For F being such a representable thing. H as of, what's my notation here? H as of X, for X being a weakly smooth scheme over S. Okay, why is that enough? Again, a priori, you have to have any, you will want to get any pre-sheaf here. But all these pre-sheaves are sifted colimits of representables, and sifted colimits are in particular contractible. So that is this reduction step. Yeah, so it boils down to now being a relatively concrete assertion about how this X and its, X special fibers and generic fiber in some sense look like. Yeah, so I will write now as before, basically XU will be X times SU, and XZ will be X times SZ, and so on. And so now let's try to get an idea what this statement here looks like. In this case, by the definitions of these functors, we can simplify this diagram. So let's say diagram star simplifies as follows. So we have at the top right there, we have the motive of X, if you like. Yeah, so maybe here I wrote H as of X, and now I write M. So I'm treating them interchangeably because we are at the end of the day asserting that this is a co-limit in here. Yeah. So let me write it like this. So MS of X. And then here we have inostar of MZ of the Scholbach to Z. Okay. Here we have MS of this XU, right? That's what this J lower sharp J alpha star does. And then here we have MS of just U. Okay, so we are, and we want to show this is a push out. So concretely, to see this is a push out, what we will now do is the following. So we will introduce this sort of, let me write it down. So we define the following thing. So H as upper Z of X. So it's basically the push out of these three guys, but for the moment I will treat it as a pre-sheaf only. So HS of X pushed out over HS of XU with this guy here, HS of U. So if I write it this way, then I want to understand this as a pre-sheaf on weakly smooth scheme. So no sheafification has taken place so far. So this would be the put out of the same diagram, but with the H's instead of the M. And so the claim is then we have to show the following thing, that this guy here, which maps to this one here, I low star HZ of X of XZ, this we need to show is an isomorphism iso after applying this Motivic localization. Yeah, so we can contemplate these constructions on the level of these species, but the only thing we claim is after doing this Kronis-Nevich machinification and a one localization, this becomes an isomorphism. Okay, and that's what we have to show. So this is the only if. Good. And now there is again a little bit of this little bit boring technical details to reduce this to some more somehow concrete assertion. So I will skip a few steps here, but which are really not, which are again very unspecific to this entire situation. And I will say the following. I will just say one reduces this to the following, also to the following. One reduces this in some formal way, formally to the following. Where I again will use some notation first. So the situation now is the following. So we have our original closed embedding, and we have this X, which lives over S, and we are given a certain section T like this. So this is supposed to be a commutative diagram. This was the original closed embedding. So where does this section somehow come up? I just say it orally. It comes up as follows. So we are trying to show that this map is kind of nice. So almost an isomorphism, in the sense, an isomorphism after applying this localization. What one does is you take a general scheme over S, map it into this, and then you hope and pray for the best that somehow every section of this guy up to these somehow processes here lives uniquely to a section there. That's kind of the thing. Yeah. So this is where this T at the end of the day comes from. So I refer to the notes for the details how this exactly works, but this is not very somehow not very meaningful now. But in this situation, we define, so for such a thing, we define the following pre-sheaf. So HS of X comma T. Yeah. So it takes as an S scheme as an input and produces for you a set. And it admits two equivalent ways of defining it. So we define this as follows. So H S of X comma T. So I want to evaluate it on some Y. So Y will live over this S here. And so there's a case distinction. In one case it's boring, namely it's just a single point if this YZ, this fiber of Y over Z is empty. In other words, if this Y happens to live entirely over U already, then we just declare it to be a point. Okay, that is the boring case. So the reason why this boring case comes up is kind of that we, it comes out from this kind of push out there at the end of the day. But anyway, in the interesting case, it's the following. So it's maps from Y to X. I'll write it down in a different way in a moment, such that if you pass to the special fiber, you get basically the section that you were already given. So let's say it this way. So YZ maps to Z. And then you have this section T here. So that's what this is if YZ is non-empty. Okay, so let me try and unwind this expression here. This is maybe not very easy to parse because it's a bit unusual. So this is somehow maps from from y to x that live over S, okay, such that if you pass to Z, then you get this pullback. And you want this composite to be related to the original section. So this YZ lives over Z, of course. And we have this map from Z to T, from Z to X. And in other words, we have a map. We have this map here. By putting the identity in the Z component, we get such a map. Okay. And we want this to be commutative. Yeah. So we take maps F that kind of extend, if you wish, in some sense, this given section. So this is what we ask it to be in the second case. Yeah. So this looks like a bit crazy because why would you contemplate such a thing? But it turns out this is exactly what you have to do in order to handle this thing. So and now let me say what. Let me give another another way of describing this pre-sheaf, which makes it more apparent that this actually is a pre-sheaf, without checking all these cases too much. So this thing there is the following equivalently. We can say the following. So this crazy pre-sheaf is the pullback of what? So we have here a 1 point thing. Then here we go to, by means of this given thing T, we go to I lower star HZ of XZ. And here we have this push out that we contemplated earlier. So HS of X pushed out HS of XU, which H with HS of U. So if you unwind all the formulas, you see this is the pullback of these kind of things. Yeah. And so maybe that kind of helps related to this discussion better. So we want to basically see that this is almost isomorphism, and this kind of measures in some sense the fibers of this map, and we are trying to show now that this is almost contractible, almost in the sense it will become contractible after applying this L mode. Yeah. The thing here. So let's let me say this. So I wrote one reduces this formally to the following. So I now have defined this thing, and now maybe let me restate the sentence. So one reduces this assertion here. So maybe let me call this double star. Double star formally the following assertion. So maybe I call this to the following. The next proposition is that this HS maps for T, so this maps here, and I claim this is an isomorphism after applying this L load. Okay. Yeah. So I'm skipping over some details, but I assure you these are the kind of the formal nonsense boring thing, and now that is something that we will have to really give an argument for. Yeah. So it's okay, and maybe to sort of convince you this is not just complete nonsense. I want to highlight a special case of this assertion, yeah, for you to see what this kind of roughly means. So special case. Let's assume, so this X, I mean, I said it. Yeah.
Double star.
Double star was, I just erased it. Double star was basically the map that this here, this alpha is an iso after applying this Motivic localization. Okay, so that was our original claim, and I claim that up to small technical formal points, you will want to check that this is the case. Okay. Good. And now I want to, before going into the proof of this, I want to highlight a special case of this to show you somehow a little bit the nature of that statement. So I remind you, we assumed that this X was weakly smooth. So this was weakly smooth. And now I want to look at a special case. So consider the special case where this X over S is not just weakly smooth, but actually weakly étale. Okay, that's certainly a case that we have to understand. And on top of this, I want to assume that this closed embedding between these affine schemes is a Henselian pair. Okay, and now let's try to get a feeling for what that meant is. So HS of X T of S. So let's evaluate it on the base scheme. So we look here. So Y is equal to S now. So we are talking about sections of the map from S into X, such that this is the case here. So then, yeah, so let's say this is this of the following. Then we have this Z sitting inside, or maybe I read it this way, Z sitting inside S. This X is my weakly étale thing there, and I'm already given this section, right? This is what I'm already given, and I want to have an extension of this section. So how do I write it best? Maybe I write it like this. So certain section sigma, whose restriction back to Z is the given section. Yeah, so sigma such that sigma Z is the original T. Okay, that's what I can consider, or what this boils down to. And so in some sense I'm saying, that's what we will have to look at here. And so now I'm claiming this is actually, there is only one such section. So why is that? Well, this comes out of this unique lifting property for weakly étale things. So another way to write this thing here is to, how do I write it? I mean, maybe I write it like this. So S is equal to S, and here now we have this Z. So this is my I, and we have this T, that's what we are given. And this sigma that I'm looking for is the thing that fills this diagram like that. Okay. And so indeed there exists exactly one such sigma by the characterization of weakly étale maps by, let's say, by a Henselian. Okay, so this is kind of what this Henselian lifting buys you, that the evaluation of this crazy thing here on the base is indeed just single function. Okay, so I hope this gives you some feeling why this this is now not a formal thing that you can expect always to be true, but here we see that it's more or less equivalent to this weakly étale. Okay? And so the argument is now a little bit more delicate than this, but basically it's similar. So this X is now not weakly étale, but rather weakly smooth only. That's one difference. And the other difference is that we don't have this luxury of assuming this is a Henselian thing. Yeah? So we have to work a little bit more. And I will now say something about these arguments. And I will actually follow for that part this paper by Motivic and Wolf that I mentioned. So they have they do what I will now do in this slightly more special case, that this map from X to S is the composition of a smooth map and a weakly étale, as opposed to this more general weakly smooth. But it's really the argument. And so to make this argument, I need a lemma first. So this lemma is kind of the, if you like, the brother or the sister of the statement we are trying to prove on the small side. So let's consider weakly étale affine schemes over S. Okay, so as opposed to this weakly smooth, yeah. So this is kind of we don't allow affine spaces here. And now let F be a sheaf for at least the Kronis-Navitch, maybe even the pro-étale topology, but at least Kronis-Navitch on this kind of small. Well, I would like to call it small side, but it's really not so small because these objects are not necessarily finally presented and so on. But anyway, maybe I can still say small side. So let's take a sheaf of pointed anima, and then there is a fiber sequence as follows, so which is very close to the localization theorem that I erased. So J sharp J upper star F maps to F maps to I lower star I upper star F. Okay, that's the statement. So this is a fiber sequence in here, yeah? Where now these functors mean what they are supposed or what they have to mean in the context of this smaller side. Yeah, so I do all these constructions, not now on the weakly smooth, but just weakly étale. Yeah. So this lemma is almost identical to the lemma in Van Scholze. So let me maybe I think I do want to give the argument here. I mean, it's their argument, but I want to give it because I want to again highlight sort of that this Kronis-Navitch is the one that you want to see here. Okay, so the proof is, however, otherwise similar or pretty the same as what they do. So I will again give the key things and gloss over some formal nonsense part. Okay, first of all, we have to compute what this is. So this I lower star I upper star F, we evaluate it on some weakly étale scheme here. And what is it? Well, if you do the I lower star, then you have to evaluate the I upper star on the pullback. I mean, this is for free. But what is not for free is that you can still say what this is very explicitly. And this is F evaluated and the hensization of VZ. Yeah, so I remind you what this is. So this V is going to be a weakly étale over Z over S. So therefore, this is weakly étale over Z, and this hensization takes such a thing and produces for you an int étale scheme over S again, whose fiber was the original one that you had. Yeah. So this is what we discussed last time. So maybe, yeah. In other words, this thing here turns out to be computable, and the reason why that is true is again because of this ability of lifting weakly étale things from Z to S. Yeah? So this hensization is kind of the key thing here all over the place. And now so that's what this right-hand term looks like. What is the other thing? This J lower sharp J upper star F is the Kronis-Navitch sheaf associated to what? You take such a weakly étale thing again and send it to F of V if V sort of lies over U completely, or otherwise it's the singlet. Yeah, so it's here where we use this pointedness, otherwise we would have sort of trouble. Yeah? So but this pointedness gives us that. So it's in some sense, if you like, the extension by zero of that. So this would be the extension by zero as a pre-sheep, and then this thing is the protonated sheep associated to this. And so now how can you hope to relate this thing with that guy? The key is now the following thing. So key point is the following. So we have this S, we have this U, and this over here we have this V. Okay. Yeah. So that's what we said, and then we put the VU here. Okay. So far so good, and we have the Z. Okay, and I now can put, of course, the VZ here, which would be the pullback. I mean, certainly it is. But this has this hensization. So I write it here on top. Hensization of this VZ. Yeah, so this is no, this is sorry, this is not a great way to write it. Well, yeah. I mean, sort of, so let's say star else. There's some more space, and here we put this hensization of this VZ. So this is once again this intertal thing over here, which has the property that its special fiber is actually VZ. Yeah, so this is again a pullback diagram. So what does this? So this is coming, and yeah, this is, as I said, proton. It's really a filtered colimit of entire maps. And the key point is now that the connection of this VU and this hensization, VU together with this hensization of this special fiber, this maps to E, and I claim this is the protonated Scholbach. Okay, by the definition of this protonated topology. Yeah, so I remind you, this was consisting of, I mean, these distinguished squares, which are kind of, you have an open, so that's the open, and you have something proetal, such that on the complement of that open, you get an isomorphism, which is exactly what we have here. Yeah? And so if you drop the word pro, then you cannot run this argument as is, because then this hensization, well, it will not be etal, but rather only ever proetal. And so that's why this pro Nisnevich is actually more easy to handle than the Nisnevich thing, actually. But a similar sort of, I mean, I'm saying this here, but this can be tweaked to make it work for the Nisnevich topology as well. Yeah, so, but it turns out to be actually easier if you give yourself this freedom of doing these hensilizations. So this is the key point. We have this covering, and now we are trying to show, this kind of exact sequence, you might call it. So we want to put a V here, V here, V here, and sort of see that we have a fiber sequence. And basically, now that it follows that if you unwind this sort of, you compute sections of a sheaf by using this particular protonated cover, and you see this VU is already in a good shape, because that tells you can easily compute it for this J lower sharp and also for the I low star. So that will be an easy thing, and this hensization will also be good because its special fiber is the original thing. Yeah, so this is kind of what's going on. So I think this I will not now unwind in all detail. So if you like, in the notes I wrote more about this. That's the key thing. Yeah, so this Pronis-Navic topology allows you to take something on the special fiber and to make it proetal over your total space in some sense, and that is what makes this work. Yeah, so that's why we could not, let's say, take pros are risky or something like this would not make this work. Yeah, so we see really it's kind of a fine combination of all these properties. Okay, good. So we have this kind of the statement that we want to have, but now on these small sides. Thanks to that freedom of doing the installation. And now we'll be able to boot relatively quickly. So as a corollary, the functors, so I consider this again, Grove-Nesnevich on this small site. And I now can take anima or pointed anima. So let's put the bullet in parentheses. And I can go from here to, so I do I upper star and J upper star. So they go to chiefs, again, Grove-Nesnevich. Similar, but over Z and over S. Okay, and I say that these are jointly conservative. Why? Well, because so you have a map from F to F prime, let's say. You want to check its isomorphism, you know it's an isomorphism here and there, and then the long exact sequence of homotopy groups for such fiber sequence tells you this is okay. Yeah. So these are both together are jointly conservative. So that's what we will now use. And now we can finally state this proposition, which I have erased. Yeah. But that was this last remaining thing. So it's the following thing. So X was this kind of nice how to say it? Nice scheme that is pro-etal plus an affine space. So this is what we saw. So it's spec A conjoined subset B and then the sensibilization mapping to S, which is spec A. So this is what I called standard weak Leotard. Yeah, sorry, standard weak move. Yeah, so we fix this. And now I'm claiming the map H S of X T. For this section, so again, X lives over S, we have this phi here, we have this section T. This here mapping down to a point is an ISO after applying this L-node. Okay. That's the last nail in the coffin of the normalization theorem. And now we can see how this goes. So again, it's a little bit somehow tricky in the detail, but I think the key geometric argument is relatively clear to see. So the proof is as follows. So we have this. Yeah, so this is what we want to show. So we will break this into two steps. So we will consider the following. We'll consider X prime over X over S. Here we have Z again. And consider this kind of situation. So we have this diagram and we put, so let's say I call this F, and then I call this T. So T will be F of the T prime. And we assume that, yeah, so consider the situation, and I can then contemplate the kind of, the differences between these things. So X prime, T prime maps to this HS XT. Yeah, so, and we call this maybe, I call it alpha for some reason. So we have such a map, which, once again, sort of wonders, given something over S, you kind of wonder how you can extend these sections to things to sections over S altogether. So we have this, and now we will make two claims. Claim one is if this F is int etal, then alpha is an ISO after applying this Grove-Nesnevich sheetification. Okay, claim number one. Claim number two is if F is of the form, if F is basically some possibly infinite dimensional affine space over S, any cardinality, then alpha is an iso after applying the other components that magnetic spaces are sort of characterized by only this A1 localization. Okay. So these are the two claims. If we have both of them, we have our original claim, because then we can put the x prime to be our original x, which is int et al. over this big affine space. Yeah, I remind you, this superscript h stands for a certain tensillization, which in particular is an int et al. Map. And so then we get this. Okay. All right. So that's what we have to do. And the harder one is that one here. And the easier one is this 10-2. So let's see how this goes. So proofs of frame one. Yeah, so you should think of this as, once again, being similar to this special case that I mentioned earlier. Earlier, I talked about this case when this x prime was int et al, and I had this extra assumption about this being Henselian. So now we have basically just dropped that extra sort of luxury assumption, if you like. So here's the argument. So we have this. These are two free sheaves. We claim these become isomorphisms. This becomes an isomorphism after sheetification, and we can observe that sheetification commutes with restriction to the small side, of weakly et al. Inside weakly smooth. So we can, for the purpose of this argument, sort of evaluate these two pre-sheaves on some scheme and then only care about the weakly et al. Side. So pick some T, which is one such test scheme. Okay, we want to evaluate these on all these test schemes, and we will show that alpha restricted to this small side of weakly et al. Things over T is an iso after applying L, this Pronis-Levitch sheetification. That's what we do. And we will use this lemma that I just erased, which concerns this conservativity. So using the conservativity of I upper star and J upper star on sheaves Pronis-Levitch on these small sides due to Bad Scholze, like I said, it suffices to do this sort of one by one. So let's say we use the conservativity like this, and so let's do that. So we can take the following. So J lower sharp the upper star of alpha. What does this do? So this really, you take your general thing which lives over T, which in its turn lives over S, but you just restrict it to U and then go back. Yeah? So this concerns basically you evaluate this map here only on schemes which are entirely living over U. And this is an isomorphism since the evaluation of these HS blah 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 is just point on any y or any y that lives over U. Yeah, so I remind you, there were these two cases. In one, there was a boring case where this was trivial, just a single point, and that was this case. Yeah, and so that's telling us we don't have to be concerned about the restriction of this thing back to U. So that is kind of guaranteed to be fine. The other thing is the interesting part. So so we check now that I lower star, I upper star alpha is an ISO. Okay. So again, we will use that this thing can doing I up star, I lower star can be computed by evaluating it on sections, namely as follows. So I lower star, I upper star alpha of some test scheme W was this alpha of this tensillization of the special fiber. Yeah. So once again, we restrict to the special fiber, and then the tensillization kind of spreads it out a little bit into something in a tunnel over S, whose special fiber was the original thing. Yeah? It's kind of a thickening, if you like, of this special fiber, but thickening in the nice sense of being in the tunnel. Okay. And so we have to see now. So we claim this. Claim one means the following. We have this first equation, and we evaluate it on this tensillization of WV, and we barely want this to be the same as the same for the X. Yeah, so here I'm really claiming, or let's say that way. I'm claiming this now honestly a bijection, and that will tell us this claim one. That's the last thing that's missing. And now this is actually it's not actually easy. I mean, after unwinding everything. So let me try and say what's going on here. So we pick an element G in here. So what is that? So let's draw some diagram. So we have this X prime living over X, living over S. And then we have this test scheme T here, which was just there to sort of reduce us to these small sites so that there's no particular relevance. And then over this we have this W, which is an element in this small site. Yeah, so this is any affine. Well, yeah, I guess, but more broadly, maybe I should say weakly smooth, and this is weakly atile. But this is not relevant right now, just for you to sort of see what I'm talking about. So then here we have now this tensillization of this fiber, and we are given so this thing here meant in particular a map from here to there, an S scheme. So this is commutative, and the extra condition was something nice works when I go back to the special fiber. So let's draw the special fibers. So here we have XZ, X prime Z, Z. Okay, here we have TZ, WZ, and now this is the same as the special fiber of this tensillization. So that's an isomorphism, and this is with GZ. Okay, and this map G was supposed to be such that this is actually commutative. Yeah, so this GZ is basically this section T here up to sort of putting it in this diagram. Okay, so that's what this is exactly what it means for an element G to be. These are maps like this making this here commutative. And now we also have this map T prime, right? That's what we are initially given. This T was this composite. So in other words, this part here is commutative by definition. And now the key thing is, I claim there is a unique map gamma. So let me write this down. Maybe here. Well, I claim there is a unique extension of this gamma well, this is easier. So this gamma, I mean, it sounds more complicated than it is. This is really just you go here, tuck, 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 and then this. Yeah. So this gamma is basically, I mean, how to write but given by this T prime. Yeah. So maybe I should not emphasize this too much. So this gamma is just this entire composite. So maybe let's say rather let gamma be given by this. Maybe that's better. So I think this makes it otherwise too ambiguous what's going on. So this is this gamma, and now the thing is that's where the interesting thing happens. So I claim there is a unique map like this. So there is a unique map. Maybe I call it delta. Delta, whose restriction to this gamma. Why is that? Well, this is exactly the universal property of the hensellization by the universal property of the hensellization. Let me write it out. So this universal property is maps from this hensellization into some int-etal thing like this. Yeah, so this is int-etal over X. Maps like this are characterized by what they do on the specifier. So this is the same as form over Z from this specifier. We're almost done. Maps, so we have a map like this, of course, but given by pullback, but the hensellization is exactly making this. I mean, that's the universal property. And of course, now we can say this is the same as form from WZ to X prime Z. Yeah? So and here we have this map gamma, and there's unique extension of that lift to over there. Yeah, so that's the thing. So it's somehow a boatload of different things, but once again, I want you to sort of take home the crux of the story is really once again the universal property of the hensellization and what we used before, that the hensellization together with the restriction to this open was then pro-Euclidean tuple. Yeah? So that makes this work. And that gives us this claim 1 and this claim 2. Maybe I will just say this very briefly. So claim 2 is much easier. And it's here where we use the A1 localization. So think this was in an affine space, possibly of infinite dimension over this. Then we have a section, so the 0 section, right? And so we get a map the other way. Of course, one composite is the identity, the other one will not be the identity, but it will be A1 homotopic to the identity by sort of rescaling the coordinates of that relative affine space. Yeah? So let me say it this way. So F has a 0 section, and this yields an inverse to our map alpha up to A1 over 2. Yeah, so A1 acts on this big affine space by scaling the coordinates, and at 0 you get the 0 section, at 1 you get the identity, and so that's why you get an A1 between the identity on the big affine space and the 0. Yeah. So that is so what I like about this, you clearly see kind of that both of these localizations have to be there for this argument to be working. And so when it comes to generalization of this, of course, people have really tried hard to generalize this to other contexts of geometry. And to my knowledge, so far no one has succeeded in pushing this beyond something like this, because somehow this A1 invariance is really crucial somehow. Yeah. So that is the status of the